Video, we're going to talk about projectile motion so that by the end of the video, you can analyze problems that involve a projectile, both launched horizontally and at an angle. So let's talk about a horizontal launch. All right, so let's say we have a building and the building is on the ground and we have two people fighting on top of the building. This person is going to shove this person directly straight across that building. What's going to happen to this person? Well, as soon as he leaves the building, he's in free fall. So he's going to start to move down. However, this person was given an initial push. So he's still going to continue to move to the right as he falls. So if I was to draw this, this is the initial push. So he gets pushed off the building right like this. However, as soon as he leaves, gravity starts to pull him down. So gravity starts to pull him down just a little bit at first. But as he falls, he continues to move to the right. And he continues to move to the right with the same horizontal speed as before. However, vertically as he falls, he starts to pick up speed because gravity is pulling him down. But as he falls, he continues to move to the right with the same velocity. But as he moves to the right, gravity brings him down until he hits the ground. So these arrows represent his velocity at the different points. So this is his initial velocity straight across. As soon as he's in free fall, gravity starts to accelerate him a little bit vertically, but he continues to move to the right, and then gravity accelerates him down even more. So he's moving even faster, but he continues to move to the right, and then finally he hits the ground. So overall, the path this boy takes looks like this. So overall, his path is very parabolic in shape. Now, let's label a few things. The distance from where he starts to where he lands. This distance is called delta x. This is sometimes called my range, how far he goes. This distance is his vertical change in height, and we'll call this delta y. About projectile motion. Projectile motion is motion in both the vertical and horizontal planes. Horizontally, there are no forces stopping his motion. So the object moves with a constant speed. Vertically, however, the object accelerates due to gravity. What's the same, however, is time. Time will be the same in both the horizontal and vertical motions. So even though they are different and they behave differently, the object is in the air for the same amount of time. So as long as it's in the air, it's also going to move to the right in that same amount of time. So how do I use this information to solve a problem that is launched horizontally? So let's look at an example. A ball is thrown horizontally at 15 meters per second from a height of 10 meters. How far will the ball land from the base of the cliff? Okay, so if we look at a picture, here's the cliff, here's the ball, and the ball is thrown straight across at 15 meters per second. The ball is going to go like this, land and hit the ground, and we want to know how far does it land away. We want to know delta x, knowing that it was 10 meters above the ground. So to solve a projectile problem, I like to split it up into two directions like we did with the vectors. So this would be the horizontal motion, and this would be the vertical motion. Horizontally, we only ever have one equation that we're ever going to use, and that's the equation for constant velocity, which is delta x equals vt. That's because, again, there are no forces horizontally to stop my motion, so I move with a constant speed. Vertically, however, I cannot. Vertically, I have to use one of my kinematic equations, which are all of these. Now I'm going to use delta y because we're talking about the vertical motion. So I'm going to use one of my kinematic equations to solve for the vertical. Now it just depends on the information I'm provided, which one I use. Now the one thing that is the same is time. So this question says I'm thrown horizontally. So that means this 15 meters per second is my horizontal velocity, not my vertical, because my vertical would be what's going up and down. This is the ball being thrown straight across, so that is my horizontal velocity. Now, I can't solve for how far because I don't know the time. So maybe I can use the information vertically to solve for the time. Let's see what I know vertically. I know that the ball has to fall 10 meters. So that's going to be negative 10 meters as my delta y. I know that gravity is going to accelerate me down, so I'm going to use negative 9.81 meters per second squared for my acceleration. Now here's where the catch to my problem comes in. This ball is being thrown straight across. So what would be its initial vertical velocity? And the answer is 0. And that's because my object wasn't moving up or down to begin with, it was moving straight across to begin with. So my initial vertical velocity is 0. And we want to see if we can find time. Because if I know the time, I can use the time horizontally to figure out how far we went. And the answer is yes, I can. I can use the second equation. Delta y equals VIT plus 1/2 AT squared. Negative 10 equals 0t plus 1/2 of negative 9.81 t squared. So negative 10 equals negative 4.905 t squared. Doing some math will tell me that my time is, I gotta put this into my calculator, 1.4 seconds. Now I know the time is 1.4 seconds, so I could plug the time into here, and I get that my horizontal range is 21 meters. So my ball will fall 10, but travel a total horizontal distance of 21 meters. And that's how we solve a horizontal launch problem. Let's try another one. A ball rolls off a table that is 2 meters high and lands 5 meters away. What is the horizontal velocity of the ball? All right, again, if I draw a picture, the ball is going straight across, and I do not know, but I do know that it will land 5 meters away, and it starts out 2 meters above the ground. So let's use this information to solve. Now again, horizontally, I only use one equation and one equation only, and that's delta x equals vt because it's constant velocity. And I know my delta x. I know how far it's landing away. It's landing 5 meters away. I'm trying to find the horizontal velocity, but I can't find that because I don't know the time. So let's see what we know vertically to see if we can find that time to help find. So vertically, I know the acceleration is not negative 9.81 meters per second squared because gravity is bringing me down. I know since my ball was originally moving straight across, the initial velocity is 0 meters per second. And I know my delta y is negative 2 because it falls 2 meters. And I'm looking for time. So just like before, I can use the second equation to figure out my time. Negative 2 equals 0t plus 1/2 of negative 9.81 t squared. Negative 2 equals negative 4.905 t squared. After some math, we get that my time that it takes the ball to hit the ground is 0.64 seconds. So we're going to use that time, plug it in over here, and I get that my horizontal velocity is 7.83 meters per second. And that's how we use a horizontal launch. The key to a horizontal launch is to know that my initial vertical velocity will be 0, and my initial horizontal velocity will be whatever it rolls off the table with, and I just plug in things where they go, remembering that my horizontal velocity or the horizontal motion is always constant velocity and always uses the same equation. Now, how do we solve angled launch problems? These are a little bit different, even though the concept is the same. So let's say we have a cannon that's being launched up at an angle theta. Now, if you remember from vectors, we do not like to have something like this. We like to use the horizontal and the vertical components. So in order to figure this out, I first would have to resolve. So the first step in doing a horizontal launch is to resolve. Resolve the vector. So to resolve, we take the hypotenuse, which in our case is VI, and look at the side I'm looking for. I'm looking for the x component, my horizontal component. And my horizontal component is adjacent to my angle, and adjacents use cosine. My vertical component would then use sine because it's directly across. Now let's look what would happen. So this is my initial velocity. My initial velocity is comprised of a horizontal component and a vertical component. Now just like before, the horizontal component does not change. So as the object travels, the horizontal component would stay the same. However, my vertical component will change because of gravity. Now think of an object that is thrown up into the air. As the object gets thrown up into the air, it first starts by slowing down. But as it slows down, as gravity starts to fight against it, we continue to move to the right until we reach my highest point. Once I reach my highest point, my object will start to fall, but I continue to move to the right, and eventually I come back down and hit the ground. And as I fall, my object speeds up. So overall, we get this nice looking parabola. If you ever seen like a football being kicked, it makes that parabola shape, and that's why. Because as it travels, the horizontal velocity stays exactly the same, but my vertical velocity slows as it goes up and gets faster as it comes back down because of gravity. And this is the principle behind an angled launch. Now, how do we solve problems? Let's look at an example. Let's say a football is kicked with a velocity of, let's say, 15 meters per second at an angle of 30 degrees. How far does the football travel before it lands? Okay, so essentially what's happening is we got a football that's being kicked with a velocity of 15 meters per second at an angle of 30 degrees, and we want to know how far does it go before it hits the ground again. Now, the first thing we need to do is we need to resolve this vector. I want to figure out what is the velocity in the x direction and what is the velocity in the y direction. Unlike with horizontal launches, where it's going straight across, angled launches move both to the right and up and down at the exact same time. So the first thing I have to do is resolve to figure it out. So the first thing I need to do is figure out the x and the y component. Now the x component is adjacent to my angle. So the resolve, hypotenuse times cosine of the angle. The y component is directly across from my angle, so hypotenuse times the sine. Now taking out your calculator, making sure it's in degree mode, 15 times the cosine of 30 is 12.9, and 15 times the sine of 30 is 7.5. Now these are the velocities I will use to solve the problem. So I'm going to go on to the next page. Remember, our horizontal velocity was 12.9, and my vertical velocity was 7.5. So I'm going to make my chart, have a horizontal and a vertical. The horizontal always uses the exact same equation. Remember, I am trying to find how far delta x. Now, here's how it's different. Before, we were going straight across. So all that velocity was horizontal, pushing me straight across. However, here, my initial velocity is actually split up between the x and the y components. So instead of using 15 as my initial horizontal velocity, I'm going to use 12.9 because that is the horizontal component of that velocity that's making it move to the right. But I can't find delta x because I don't know the time. So let's see what we know vertically to see if we can find the time. Now I know the acceleration is negative 9.81. We're in free fall. I know my initial vertical velocity. Now before with horizontal launches, my initial vertical velocity was 0 because it was moving straight. But again, here we're moving up as well, and we're moving up with a velocity of 7.5, our vertical component. So my initial vertical velocity is 7.5. I'm looking for time. Now there's one more thing I know, and that is my delta y. Now here delta y was easy to see because we fell 2 meters, or in this example we fell 10 meters. But look what's going on. My football starts on the ground, and it lands on the ground. Delta y is my change in height, or my change in vertical displacement. I start on the ground. I end on the ground. So my delta y would be 0 because I start and end on the ground. My vertical height does not change from beginning to end. So again, I'm going to use the second equation because we like to use the second equation when it comes to projectiles. 0 equals 7.5t plus 1/2 at squared, where a we know is negative 9.81. All right, and with some math, we get this. And this is a quadratic, and the only way to solve a quadratic is to either factor quadratic equation or put it into your graphing calculator. But lucky for us, we could factor this one by pulling out a t, because t is common to both. So either t equals 0 or 7.5 minus 4.905t equals 0, which means that time is either 0 or time is 1.53 seconds. Now, obviously, it makes sense for time to be 1.35 seconds. So delta x is equal to 12.9 times 1.53. So my displacement is 19.72 meters. So my football travels 19.72 meters before it hits the ground again. And that's how we look at an angled launch. So I want you to spend some time solving these examples. We will practice some more problems tomorrow based on projectile motion.